Good afternoon, everyone, and welcome to this workshop. It has been organized in the framework of the RuralBioUp European projects, aiming to aiming to meet several different projects involved in the bioeconomy, and especially on a particular aspects of bioeconomy, that's the nutrient recycling in the soil. Because we all know that soil is one of the pillars of the environment, and the health of the soil is the health of the environment, and it's of particular importance to supply organic matter to the soil, and is of a particular importance in a general view of circular economy to supply organic matter arising from waste and residues of agricultural, agro-industrial, and other activities based on biomass. So, we have this afternoon 8 different presentations from, as I said before, different projects. And I'm sorry because I know that is not very kind from me, but we are short of time, and I ask any speaker to stay within 10 minutes. I have a timer with a ring that yes, a ring that will ring soon after 9 minutes, so you will have 1 minute to close your presentation. So, without waste any more time, I would invite the first speaker. That's Leonora Pettinari. Who is Leonora Pettinari? Whose speech is on anaerobic digestion of agricultural residues and biomethane and digestate production from the biogas plant of Osimo. Please.
Okay, so good afternoon. You see me?
Okay.
Okay. Okay. So good afternoon. Thanks to inviting me today at this interesting
Please,
workshop.
can you put on full screen your presentation?
Okay. Okay.
That is better.
Okay, it's full screen now. Okay, so good afternoon. Thanks to inviting me today. I'm speaking about the anaerobic digestion of agricultural residues, biomethane and digested biogas plant Osimo. We are in Marche region, as you see, exactly in Osimo, a little city near Ancona. And I want to talk today about how we have created a short supply chain in biogas sector, how we want to improve in the future by switching to biomethane. This is a picture about SGR Biomethane Group that acquired the biogas plant in 2024. And they are working on biomethane sector, and they are trying to improve the sector so that they can introduce green energy. And also our biogas plant will be from electricity to biomethane in 2026. The plant was born in 2012 and was born by an agricultural cooperative that has two plants in our region that produces frozen vegetables. So that they had the problem to use first vegetable byproducts, and then these byproducts became a resource for biogas sector. Okay, you can see some picture about the plant. Now we are producing electricity. The power generation is more than 2 million kilowatt hour of electricity, and the plant now has a cogenerator engine. In the future, in 2026, the plant will be converted to biomethane so that we produce biomethane instead of electricity. This is how it is now, and then that's how it will be in future. So from the biological process of anaerobic digestion of organic substrates is originated raw biogas, a total green fuel composed of biomethane and carbon dioxide. Through the upgrading system, biomethane will be separated, and so we'll have biomethane to sell to the public grid. So is a picture how it will be in future. You can see raw materials that we use now and what we'll use in future. I have to say that now the raw materials are silage, poultry manure, and vegetable byproducts. I have also to say that silage is not from first crops, but came from local farmers as second crops, while vegetable byproducts come from regional plants, and also poultry manure. You see the percentage of what we do now. In the future, you can see that we use more or less the same raw materials, but percentage will be changed because we have to we'll have agricultural byproducts, we'll have poultry manure, and they increase the quantity. The amount, sorry, and the silage will be reduced to 30%. I have to say that we use only local byproducts so that a very good circular and sustainable short supply chain will be made, will be increased with biomethane after 2026. Here is an example of what we'll do in the future. We start from the anaerobic digestion. Anaerobic digestion will be from wastes, agricultural feedstock, and after fermentation, after the digestion, we will produce biogas that will be converted to biomethane with the upgrading group. We'll have, for example, biomethane for grid, biomethane for vehicles, or also liquid biomethane. But one of the most important, at the end of this circle, we have digestate. Digestate is the byproduct of this process, and we use digestate in soils to fertilize soils and to decrease the chemicals input, so that we can have a circular supply chain where organic matter is used to have the anaerobic digestion and then came again to soils with digestate, so that we will have a sustainable and circular supply chain. Now we do it, but in future with biomethane, we will increase this chain. So is good, the biomethane will be good and electricity, what we are doing now. About the carbon dioxide, we have to say that we don't know, we don't do a pollutant process because carbon dioxide is hidden within the digested organic substrates. So we have a really green energy. At the end of this, I say about digestate, that is the byproducts of the anaerobic digestion process. It represents a portion of residual biomass that has been undigested. And the agronomic use of digestate as a fertilizer ensure the supply of nutritional elements to replace intact fertilizer. In particular, during the anaerobic digestion process, there is a mineralization of part of the organic nitrogen into ammoniacal nitrogen, making the nitrogen more ready to be used. So that you can see in this picture how we can have digestate in soils. In the first, we have liquid digestate that is more ready for crops, so that we use during a life cycle crop. It contains nitrogen more ready, while usually solid digestate is used after a crop harvest, so that with solid digestate we can increase the organic matter on soils. With the digestate, we can close the circular supply chain, so that we can give again organic matter to soils, and we can also reduce chemicals input in agricultural system. Thank you for attention. My presentation is ended.
Thank you for your presentation. Very clear and in time.
Okay.
So I just I think that if we would put some question to the speakers, it would be better to speak at the end of this workshop in order to save time. I don't know if you agree. If yes, we can continue and go directly to the following speaker. That is from who is from Acquedotto Pugliese, is Mr. Nicola Tselikas. I hope to have a good pronunciation of your name. And the item of this speech is very interesting because he will speak about the use of wastewater and sewage water in order to recover water for agricultural needs. Please, for your presentation. Non è F5, una volta è F5, chiedo scusa.
Okay, thank you so much. I'm Nicola Tselikas of the Green Strategies area of Acquedotto Pugliese, and thank you for the invitation and giving me the opportunity to share experiences. Acquedotto Pugliese is a public company the water service operator in Apulian region. And this is our operational data. We serve 260 municipalities for more than 1 million customers and 4 million citizens in the Apulia region and in part of the Campania region. And we manage more than 20,000 kilometers of water network and 13,000 of sewage network. And we manage 185 wastewater treatment plants, which produce more than 250 million cubic meters per year of treated water, and about 175,000 tons of sewage sludge. And in the treated wastewater and the sewage sludge, there are the opportunities of collaboration with the agriculture sector. Our strategic plan gives a strong commitment in pursuing actions for the protection of water resources, circular economy, and energy transition. The activity, the core business of a water service operator appears to be in competition with the agriculture sector, because the agriculture sector is a very high water demanding sector. But from the collecting of the sewage to the treatment and the production of byproduct, there are several opportunities of industrial symbiosis with the agriculture sector. One of these is the production of sewage sludge. Our sludge is compliant to the legislation, the national legislation, but pending a new European directive, the problem is now that in Puglia we can't deliver directly the sludge to reuse, because there are barriers opposed by the local community, and local authorities don't authorize us to reclaim directly sludge on the crops. There are also affairs of emerging pollutants in the sludge, but however, the good quality of the sludge permit us to deliver it in reclamation plants. The question is that of the most of our sludge is delivered to reuse, indirect reuse, but we don't have plants near our wastewater treatment plants, and so most of the sludge is delivered outside the regional boundaries. For these reasons, the priority in our investment are, of course, the prevention of production of the sludge, which is still a waste, and the preparing for a use in according to the hierarchy and pyramid of the law, which establish that the disposal in the landfill is the last and least, of course, measure to deliver our sludge. So this is in this graph we have the delivery of our sludge. Most of them, the total of the production is delivered to indirect reuse, but the problem is that there are no plants in Apulia region. In this graph, we can see we outline that until there is a decreasing trend in sludge production, but there is also a decreasing trend in the sludge directly delivered to crops, to agriculture. And so we had the permission until the 2019, but there is also a decreasing trend in the sludge delivered in local reclamation plants. In 2023, the whole quantity of sludge is delivered to reclamation, but outside the regional boundaries. ARERA, which is the Authority for Energy, Networks and Environment, evaluates the efficiency of water services operation through 7 technical indicators. One of those, the M5, sets objectives to reduce the sludge delivered to landfill. And our M5 is quite the 0%, because all the sludge is delivered to indirectly reuse. So for this reason, our investments, of course, are made to improve, to reduce the quantity of sludge, especially by centrifuges to increase the concentration of dry matter. And we have also planned, there are 3 sludge dewatering greenhouses in constructions to produce a sludge with the natural techniques with a dry matter of 75%. So for this reason, we are going to pursue projects to increase, to improve the local market demand. And one of these projects is the RONSAS in partnership with the University of Bari, University of Sacro Cuore and the CREA. And the so-called RONSAS is a recovery of organic and nutrients from sludge on Apulian soil in 2 wastewater treatment plants in Puglia, which are Foggia and Barletta, designed to produce up in 2023. These plants produced 8.5 tons of tons of sludge, and we aim to convert this production directly in a soil fertilizer without passing by the status of waste, because the whole quantity delivered to the reclamation plants outside the region, the Puglia, is still a waste with the code 190805. And with this project, we aim to produce directly fertilizer. This is the product sheet, and this is the layout of the facilities. With this plant, we have a chemical hydrolysis dosing calcium hydroxide, sulfuric acid, ferric chloride, to have a precipitation of calcium sulfate, and to reuse directly this product on the soil. There are, of course, this project is in progress. We have produced up of 2.8 thousand tons this year, with advantages, of course, in the agronomic production. Another question is the reuse of wastewater treatment plants in Puglia in condition of scarcity of rainfall and a control extraction. We have a big problem of marine intrusion in the ground water. And so the wastewater treatment plant can be, is of course an hygienic sanitary facility serving local community, but it is also can give us a development opportunity for agriculture sector, because it's like an oasis in the desert. There are some pictures The first one, this is the plant of Squinzano in Salento. This is the output of the plant of Vieste delivered to sea. This is the final destination of the wastewater treatment plant in Squinzano, and it is like the last picture is an idea of what a wastewater treatment plant could be. We manage 185 plants. We have a big plan for reclamation. We have 6 operational plant systems, and 29 is already configured to give to deliver wastewater treated to the crops. Of course, we have 10 years experience in producing water for reclamation. Okay, sto finendo. And the new legislation, European legislation, aim to draft a new document with a risk analysis for the reuse, because from the sewage collection to the reuse, there are some boundaries of responsibilities, not only for the wastewater treatment operators, but also for the net operator and the final consumers. This is the minimum requirements by the new regulation. Okay, this is an example of reclamation plant in Puglia, which is Castellana Grotte, and that's all. Thank you for your attention. I close with the picture of marlats and flamingos living in superficial bodies by wastewater treated, because we believe also in the environmental reuse of the waste. Thank you so much.
Thank you for your presentation. I excuse, but time is very short for us. In any case, if speakers will agree, we'll provide to share in future the presentation of this workshop, so you will have a better view of any slide showed during the presentation.
Okay,
thank you again.
Also my email address for any question.
Okay, no problem. Okay, now we go to another item. I would invite Mr. Roberto Matteo from the Cereal and Industrial Crop Research Center of the Agricultural Research Committee in Italy. I don't know the correct English translation of CREA. Okay. And the subject of his speech will be the active molecules and the sustainable farming practice. The use of biomolecules, innovative products, in order to enhance productivity and save the crops of our agriculture. Okay.
Okay.
Please.
Thank you, Vito. Thank you for the invitation. I will go straight to the point. So we're talking about active molecules, and I'll bring you our the experience of our research group based on basically on these starting from this collection of plants that is basically brassicas. And our work is on finding in this great group of plants. So we are talking about 300 of genera and almost 4,000 of species. Our work, in fact, is on finding new bioactive molecules that characterize this family, and also in evaluating the efficacy of the biofumigant plants as green manures and byproduct for soil improvers and pathogens containment for just because of its bioactive molecules. And also other features that goes from attractant for food and therapeutic potential for pollinators and many more. So we started from biofumigant green manure, so the classic approach, and trap crops that attracts pathogens from the soil. And from this first approach to this group of plants, we have moved to the finding bioactive compounds in other tissues. So starting from the seeds, you can find in different tissues of the plants, in fact, also in seeds, different kind of bioactive molecules that goes from phenolic compounds, phytoestrogens, melatonin, minerals, and many more. And if we see as a bioraffinery, the approach in extracting the oil, we have a co-product that is the seed meal or the cake, in which as well you can find bioactive molecules that can be used for different approaches. So here you can find different kind of approaches. And that can go from animal feed and functional and food products and many more. So as you can see, there's millions of tons that is basically rapeseed, the production of oilseed. And as I said before, we can also improve this production with a differentiation of plants, just not only go with rapeseed, but we're talking about, as I said, of 4,000 of species from brassica. So there's a great potential in this term. So talking about the bioraffinery approach, as we said, we're starting from the seed, and we have the fatted seed meals or cakes and the oil. So we try to use this bioactive compound, in this case for biofumigation, producing from seeds bioactive defatted seed meals, pellets, and also liquid products that can go into the soil for biocontrol and also for their characteristic nutrient components such as organic nitrogen, phosphorus, potassium, sulfur, and many more. So this is interesting also from a nutritional point of view. If we see on this material as biomasses, as fertilizer, in fact. But also we said that this bioactive molecule can control pathogens, pests, and disease in the soil. So we're talking about studies that have proven the efficacy in controlling nematodes, for example, in controlling wireworms, different types of fungi. So it's quite interesting to see different aspects of these applications. And but also we see this approach as a cropping system, as a synergistic approach that can go from the green manure, in fact, from the biofumigant green manure, from the trap crops, and also when you have the standing crop on your field, you can use the pellets and the liquid treatment in a synergistic way to complete the efficacy of these plants. But also, this system can go in more broad broad vision, using in this kind of approaches also biostimulants, corroborants, or basic substances as the regulation of the EU define them, and also biopesticides. So there is a huge system that can be exploited for this application based on the natural-based solution. And as an example of this, I'm bringing this work that we have presented in the Biosymposium of we have presented at the Symposium on Biofumigation that was held in Argentina just a couple of weeks ago. And here you can see the potato crop. In this case, we used this approach using the plants, the green manure materials, the pellets, and also different other solution that goes from the agronomical solutions. That is basically the early harvest of potatoes, and also the use of microorganisms. And at the end of the crop, so in the latest stages of the crop, we use the liquid products in order to protect the crops from different disease. And it was quite interesting to see that this system works better than the IPM that the farm used in this context. Also in this work, we're trying to go further and to evaluate the effect of the biofumigation approach to the microbial communities through different approaches of metabarcoding and so on. So from this point of view, we obtained good quality products, reducing even the waste of the production of potatoes. And then another example we worked on lately is Susincher project, in which we used brassica-based extracts for the control of pathogens of cereals, and also the potato peel waste from industrial transformation, which contain basically alkaloids that are bioactive compound as well, and was used. They were used for the control of different pathogens that produce mycotoxins on the cereal. So as you can see, there's a lot of solutions that you can use as small pieces of a big puzzle for they can be used in a synergistic way to reach the results. Another example is the extract rich in bioactive molecule as well in the control of different fungi. In this project in the Agritech National Center for the Technology in Agriculture, we approached two different kind of application. One more the antifungal activity, and the other one is the use of the peptides and the amino acids for the biostimulant activity. So another solution in terms of bioactive molecules as well from the extracts of plants. So concluding, we have different kind of bioactive molecules that can be used for the transition toward an agri-food system that is better focused on protecting the soil. And basically, we can reduce the plant protection product, the synthetic plant protection product, and increase the soil fertility and the agrobiodiversity using these different kind of plants, creating new cropping system, a new supply chain as well, and enhancing the extremely resilient and less considered crops, such as the minor crops we presented in this presentation, and also reducing and enhancing the waste and the byproduct use in the agri-food supply chain. So thank you from our research group, and we are at your service for any questions and so on. So that's it.
Okay. Thank you for your presentation. It's a very interesting example of new products for bioeconomy. So I would invite the next speaker. That's Chiara Cosenza from the Research Center for Agricultural Policies and Bioeconomy of CREA.
From Consorcio Retusa.
Sorry, no. Oh, sorry. No, sorry for my my view is okay. No, it's from, yes, I know, from Consortium Aretusa. I will jump to the next presentation. Okay, from the Consortium Aretusa. Her speech is for show some results of ultimate project and will deal with the reuse of reclaimed water in agriculture. Please, and sorry for the mistake in the presentation, but you have 10 minutes.
Thank you very much. Good morning, everyone.
As any other speaker.
Perfect. Just a few words about the Retusa Consortium. It's a no-profit consortium that it was founded in 2001 to build and manage a wastewater treatment plant to produce reclaimed water in order to optimize the use of water at the regional level. We are in Tuscany. And in 20 years, we delivered more than 54 million cubic meter of reclaimed water to Solvay. This is more or less the system. So we collect the wastewater from the wastewater treatment plant from Cecina and Rosignano. We treat this water and then we supply this water to Solvay. In this way, this amount of water is saved. Is good for, of course, for the community. Just to present the site. So you can see here the industry, Solvay, also that is the municipality, and the wastewater reclamation plant that is from Aretusa. As you can see, the Cecina wastewater treatment plant is far away, 11 kilometers. So we have to build also the infrastructure to connect these two sites. I think it's always necessary to remember why we have to talk about freshwater scarcity, because it's already affecting, we will affect even more the sectors that use fresh water most, like agriculture. In this sense, wastewater from municipal wastewater effluent is a really good opportunity to like an alternative freshwater supply. Even if we consider that wastewater from, of course, municipal effluent, it's full of nutrients that can help the soil and improve the quality of the soil. This regulation is not new. So the European regulation 741/2020 help us to reuse water. The aim is to facilitate the uptake of water reuse, and also to guarantee a safe use of this water. We are talking about risk assessment plan. In these years, the European Parliament launched the other two regulation of risk assessment. So I invite you to also read about it. It's important. It's important to specify that it's water fit for purpose concept law. It's really different in our actual law, because we have four different classes of water, and we can decide how treat our water to achieve our objective. For example, for the first class, It's a really good quality of water. We can irrigate with this water all crops that is consumed raw, and the water is in directly contact with the plant. Of course, there are parameters that we have to monitor, respect, like E. coli, BOD, TSS, but there are also others. In Italy, this regulation is not fully applied. We are waiting for the full regulation, but we have the old degree 185, 2003, and the Article 7, the law 68 to 2023. But we are waiting for the full law. But this Article 7 already speak about this kind of limits. Okay, they are a little bit restrictive in Italy. Of course, as you can see, if the wastewater treatment plant, the effluent, respect this limit, we can use this water, or there are necessary others treatment, like could be on tertiary treatment, or even if desalination. I think it's the last choice because as you know, it's really expensive in terms of cost and energy. Use reclaimed water means face new challenges. For example, I will not read everything, but for example, the low cost of the conventional water resources compared to treated water, or the distance between the wastewater treatment plants and where the water is needed, or the effective education of information of the end users and also the government, technological adaptation, and also business models and assessment risk, because it's a really important give safe water. We develop our experience in the ultimate project, also in reclaimed water for irrigation use. This is project started in May 2020, and it ended in October 2024, but our study are still ongoing. We were the case study 3 in Rosignano, together with the Università Politecnica delle Marche, Consorzio Politecnico Magona, AWS systems. Just some words. The project was about their use, the optimizing their use of water and the recovery of materials, like using byproduct in the treatment processes. But as said, we also talk about the use of reclamation water for irrigation purposes. We developed this matchmaking platform that is a support decision tool. And so depending on the quality of the water, it will be this water will be used for industrial use or for irrigation purposes. Which parameter is it's not standard, it's the conductivity. Because we are in a coastal area, so we have a really critical intrusion of seawater in our sewage systems. So as you can see, the parameters over to some respect the government, the regulation that I showed you before. We are talking about conductivity in our water that have 2,000 microsiemens per centimeter, or 3,000, even if we have peaks of 5,000 microsiemens per centimeter. So it's really a salty water. It could be critical for use this water for any use. We started several pilot tests, include reverse osmosis, of course, to reduce the chloride of the concentration in Aretusa effluent, but also to study the brine, because this is also a critical point to talk about it. About the experience, so we planted the first species, as you can see, and the second and the third species we will plant in May 2025. So we will irrigate these 3 species with reclaimed water, and we will test the behavior of the species. They are all resistant and tolerant, tolerant to salty water. There are many papers that are demonstrating it. So about the flow, just to show you the layout of the Aretusa reclamation plant, we have equalization tank where the effluent of wastewater of Cecina and Rosignano mix together, and then we have coagulation, flocculation, sedimentation, and filtration, biological filtration, activated carbon, and UV disinfection. The 4 flow are this one. So we have the first flow is the pre-Aretusa, so is wastewater already treated, but not by Aretusa. The second flow is treated by Aretusa. The third flow is treated by Aretusa and is mixed with the desalination, desalinated flow. The fourth flow, of course, is the control one with fresh water. So we, as I said before, we planted the first piece and we are testing it. We are doing the monitoring non-destructive test. But at the end of the life of the plant, we will also do destructive tests to understand the behavior and the inquinants, if there are any, in the plants. Conclusions. Okay, so the reuse of wastewater is a solution for the increasing pressure on freshwater resources. Wastewater also contribute to the promotion of circular economy by recovering nutrients from the reclaimed water and apply to the crop. The reclamation facility operators and end users should cooperate to ensure that reclaimed water is produced in accordance with the minimum quality requirements established to the current legislation. You have here the last regulation of risk assessment. And finally, the wastewater represents a precious resource for agriculture, so it is essential to overcome all obstacles in order to obtain the maximum potential of this water. So, thank you.
Thank you for showing us this very interesting example of circular economy concerning the use of water. And we'll go to the next presentation. That's about another project, the Rustica project. So I invite the speaker. It's online. Thank you. So, can you start your presentation?
Can you hear me? Do you see the presentation?
Okay.
Okay.
Can you put the presentation on full screen?
Yes, I did. Can you see it?
No.
No.
No more.
Mm. Mm-hmm.
Okay.
Control L.
So it's better.
Okay, that's my best. I think
Okay.
we have to go.
It's okay. It's okay.
So good afternoon and thank you for the invitation. Today I will present the Rustica project, which is an EU-funded project focused on bio-based fertilizers. This project brings together a strong consortium of 16 partners, as you can see in the slide, 16 partners from various countries and both academic and non-academic. each contributing expertise to advance sustainable agriculture practices. So the project is coordinated by KU Leuven, a leading university in Belgium. For Italy, the involved partner is CREA, so the Council for Agricultural Research and Economics. So together, our efforts are aimed to developing innovative, environmentally friendly solutions for the future of farming. So the project goal is to create market-ready products for the fruit and vegetable sector, but with the potential to expand into other agricultural areas. This presentation is shared with colleague Claudio Mondini, so we will take turns. The structure of the project is around 2 main pillars. The first one focuses on development of technologies for converting residues into bio-based fertilizers. And this involves advancing innovative methods to transform agricultural and industrial residues into fertilizers that can sustainably enrich the soil. The second pillar centers on market opportunity analysis and multi-actor engagement. And this includes assessing market potential, engaging diverse stakeholders, and actively listening to local communities in order to ensure that the project aligns with regional needs and promotes adaptation on a broad scale. Together, these 2 pillars drive the project's approach, combining technical innovation with the socio-economic awareness to create practical and impactful bio-based fertilizer solutions. So these are the keywords of the second pillars. I would like to start with this multi-actor approach because the project is based on this implementation in order to support networks buildings and feedback, which are essential for creative, let's say, sustainable and transformative solutions. So this approach, this multi-actor approach, aims to establish new networks and also aim to provide stakeholders with a platform to voice their needs and insights, and also to organize the value chain in a way that is both efficient and sustainable. We have target regions for evaluation, 4 regions across Europe. For Italy is Friuli, Venezia Giulia. For France is Pays de la Loire. For Belgium, Flanders. Spain, Almeria. And also 1 region in Colombia, which is Valle del Cauca. With this multi-actor approach, we have 3 levels of engagement. The first level is the consortium level. We develop guidelines to address project goals and provide also practical information on tools to be used in the regional workshops. We developed 6 workshops in each of the 5 regions. The second level is the level of the knowledge brokers, which are who reports and share the insights and findings of the regional workshops. And then we have the third level, which is made by the stakeholders. We try to encourage participation, gathering feedback, and also inviting to give inputs and direct proposals from them. With this chart, I try to summarize the 5 main blocks of the second pillar, which are developed for the 5 regions. The first block combined the statistical data with the policy framework and legal limitation and life cycle assessment. The statistical data, of course, are the foundation for understanding the agricultural practices, the market needs, also the environmental impact, The policy frameworks and legal limitation are also very important to analyze the existing regulatory environment, to navigate any legal barriers, and also to align solutions with current policies. And then the life cycle assessment, which is a critical aspect of our project. The LCA evaluates, the environmental impacts of bio-based fertilizers from production through disposal. And this assessment helps us measure sustainability and also help us to refine the processes to minimize, of course, the ecological footprint. The second block, let's say, is the analysis of the key drivers and the influential factors. They were assessed based on their level of uncertainty and importance. And these allow us to construct 4 plausible scenarios that range from, let's say, the worst to the best outcomes. We evaluated critical factors that could impact the adoption and the success of bio-based fertilizers, also including demand, the market demand, the technological needs or advancements, the policy, the environmental impact, and also the stakeholders' engagement. Then we have actors involved, key issues, business models, and applicability and adaptation. Regarding the actors involved, our multi-actor approach includes diverse stakeholders like farmers, agribusinesses, policymakers, researchers, environmental organizations. And of course, each plays a critical role in providing insights and feedback. Key issues, we try to address key issues during the progress of the project. For example, regarding the regulatory compliance, the supply chain logistics, the scalability, the environmental impact. We try to build up a framework that could potentially anticipate obstacles and try to find solutions accordingly. Then the business model, which is really crucial for this second pillar. We try to build up business models starting from value chains and then testing the robustness by the robustness check, of course, and try to also generalize the models to apply them across diverse agricultural contexts. Then the applicability and adaptation of different contexts, it is related to the market, the agricultural practices, and looking at the different regions, try to find adaptable solutions. So the local requirements are considered, and also the scalability, as I said before, the flexibility to, let's say, accommodate distinct economic, social, and environmental contexts. Maybe I switch one, sorry. Okay. The method we use for developing the business models is the Canvas model, which, as you know, is based on 9 building blocks: the customer segments, the value propositions, the channels, the customer relationships, the revenue streams, the key resources, the key activities, the key partnerships, and the cost structure. So starting from a desk analysis and project-generated data, we developed these business models for each of the 5 regions in the project. And to do that, we also use the feedback from the multi-actor meetings, so the regional workshops. Sorry. So the results that we achieved, we identified potential adopters for the Rustica bio-based fertilizer technologies for example, intermunicipal companies, farmers, cooperatives, or technology providers. Then we build up potential circular value chain configuration, and for each regions with potential adapter for the Rustica bio-based fertilizers. Then we also developed SWOT analysis for each regional business model to highlight limits and opportunities. Then the draft business models have been fine-tuned with more specific data. Okay. To conclude, the project has laid a solid foundation for developing viable business models for bio-based fertilizers by engaging players and potential investors at the regional level. This was a very important task to develop, and also challenging task. So the targeted approach that we used aim at ensuring at each region the needs, the opportunities, and also the stakeholders to be taken into account, and also looking at the scalability. And to support this, we gather detailed data on the bioavailability of agricultural and industrial residues, providing a clear picture of the resources and processes within each region. We also have outlined the technological processes required at the regional level to convert these residues into high-quality bio-based fertilizers. So finally, we have estimated the amount, the quantity of bio-based fertilizers that can be produced, giving us crucial insights into market potential and supply feasibility. So together with these elements form a robust foundation for sustainable, regionally tailored business models. Now I'll hand over to my colleague Claudio, who will present some interesting results related to the technical aspect, which is the first pillar of the project.
Okay.
Claudio, would you like me to go on with the slides, or would you like to share your screen?
I would like to share my screen.
Okay, so I'm going out.
Can you see my screen?
No.
No.
Now?
We see you, but not your presentation.
No. Can you see now? Do you see my screen?
Yes.
Good afternoon. I will present some aspects of the first pillar of the Rustica project, that dealing with the development of technologies to produce bio-based fertilizer from residues of the fluid and vegetable wastes. This process was performed in 3 steps. The first one was the development and optimization of organic wastes from conversion of organic wastes into bio-based fertilizer. And the conversion processes we analyzed were cultivation of microorganisms, filtration assisted by electrodialysis, insect breeding, pyrolysis. Composting is also reported in the list. We have not studied composting because we thought composting is a mature technology, but it's reported on the list because we use compost in the formulation of the blends, as we see later. Then the byproducts of these conversion processes were characterized and then evaluated for agronomical properties, mainly by laboratory and pod trials. And then the last step, bio-based fertilizer blends were formulated and validated mainly in field trials. The development of Rustica technologies is outlined in this figure, in this diagram, in which we can see that the wastes from fruit and vegetables were subjected to the different conversion processes according to their degradability. So the more easily degradable wastes were subjected to cultivation of microorganisms or filtration. The part more moderately degradable was treated by insect farming, while the part with that was rich in lignin was treated mainly by pyrolysis. Some word about the technology that we have studied, the cultivation of microorganisms. In a first study, there is anaerobic digestion of the wastes with a production of a solution that rich in carboxylic acids. Then this solution is placed in an aerobic reactor where selected microorganisms utilize the carboxylic acids to grow. After 3 days, the solution is centrifuged and dry, and the solid part is dried to give a nitrogen-rich fertilizer called microbial biomass or microbial protein. Alternatively, the solution rich in carboxylic acid can be treated by filtration assisted by electrodialysis to give a concentrated solution rich in nitrogen, phosphorus, and potassium. In insect breeding, the insects are grown on the residues of waste, the wastes of fruit and vegetables under controlled condition. At the end of, after 2 weeks, the substrate is dried and separated into different materials. One is the insect frax, that is a mixture of insect droppings and the remaining of vegetable and fruit residues. And the second one is the insect biomass that is constituted by the body of the insect larva. The last technology is pyrolysis, that is a thermochemical conversion of the biomass that's performed in a limited environment with limited content of oxygen. And the solid product of this process is biochar, this material characterized by extremely resistance to degradation of the soil. These materials, the products of the technologies, were then characterized and evaluated for their properties as a fertilizer. This was performed by chemical standard analysis, but also by some laboratory incubation. The fertilizer were added to the soil, incubated under controlled conditions. And during the incubation, they were analyzed for soil parameters related to the cycles of nitrogen and carbon, the availability of the elements, the microbial pool, and the emission of greenhouse gases. In the following figure, it's reported an example of the results we have obtained. This is the respiration of the soil amended with the fertilizer. We have analyzed different samples for each category of bio-based fertilizer. But besides the variation that there is within each category, we can see that all the different classes of bio-based fertilizer present a distinct impact on soil properties. So we have concluded they can be used to fulfill specific function once they were added to the soil. So microbial and insect biomass are characterized by high nitrogen content, a fast mineralization of organic matter, and a fast release of amount of nutrients. And so are many indicated as substituted of mineral fertilizer. They present a drawback that sometimes that can increase nitrous oxide emission. On the other side, insect frass are degradable to an extent that can sustain maintain biological activity, but still show some persistence in soil, so they can maintain the physical role of the organic matter in the soil. So are mainly indicators to maintain the quality and the fertility of soil. Biochar, on the other side, is characterized by a high recalcitrance of soil. So its function in soil is more to foster soil carbon sequestration and to combat climate change mitigation. So we have seen that bio-based fertilizers are effective fertilizers, but we think that they can be more effectively valorized by mixing them in a blend. Because this, with a blend, we can obtain a fertilizer with multiple function. We can reduce some negative effects of fertilizer. It's more easy to tailor the fertilizer to specific crops in pedoclimatic regions. And also if the blending is associated with process integration, then this can reduce the production cost of the fertilizer and also the environmental negative impacts. So different blends were formulated based on the characteristics of the bio-based fertilizer, and also of the needs of the regions, of the crops, and different pedoclimatic conditions. In the table, we have an example of the composition of the blends. The blends were assessed in laboratory, and then we arrived to a final formulation of the blend, and that was validated in field trials. The field trials were performed in the different regions involved in Rustica with different crops. But I will also only report about the trial we are performing in our region, Friuli, on a vineyard. We compared in a vineyard three Rustica blends with a control, without fertilization, and two reference treatments, an organomineral fertilizer and manure. Some results. We have seen that the blends have a positive effect on the soil. On the graphs, the blends are the three bars on the right, and so we can see that applying the blends have a higher impact to some important properties of the soil, such as the mineral content of nitrogen and the microbiome.
1 minute to close.
Okay, microbial biomass carbon. Also, there is a visual appreciable effect on the growth of the grasses. The grasses grow faster to a larger extent in the soil treated with the blends, and also the compactness of the cluster and the berry size is higher in the soil treated with the blend, that is in the panel denoted with A, with respect to the reference treatment and so we concluded about the field trial that the application of Rustica blend brings to an enhancement of soil properties such as organic carbon, nitrogen availability, and microbiome too. The plant productivity was compared to that of the reference, and also we have seen that we had a better quality of mast that are more equilibrated and more prone to produce a good quality one. And concluding about the technical part of the Rustica project, we have demonstrated that during the project and optimized new technologies to produce bio-based fertilizers from vegetable residues. This bio-based fertilizer can be used to fulfill specific soil function, but a more effective option to fully exploit their potential is to mix them, to make a blend, to produce innovative fertilizer with multiple functionalities that can be an effective and viable alternative to usual fertilizing products. Thank you for your attention. These are our contacts, and also in the presentation that we will be glad to share, we can find also the contacts of the project. Thank you again.
Okay. Thank you for your presentation. Very interesting about the fertilization, the innovative fertilization ways of soils. And we continue on such item with the next presentation. I invite Lorenzo Davino. He will speak of the results and the objectives, obviously, of another project, the Excalibur project, and in particular about the microarthropod ecological index to assess mycorrhizae inocula across Europe. Please, Lorenzo.
Thank you.
You also have 10 minutes.
Okay. Thank you very much.
No, we are on time and just on the line. Eh?
Perfect. No problem.
Davino.
I stand. Yes, Davino. I stand if it's no problem. So I present here some results of Excalibur project. Is a 5 years horizon project. It's very big one, coordinated by Stefano Moccali, my colleague in CREA. But we choose to focus on a particular aspect and topics of this project because it's too big to present all the results now. We talk about microarthropods ecological indices to assess mycorrhizae. Maybe not everyone know who are microarthropods. Is arthropod belonging to mesofauna. Mesofauna is the you see, it's important the body weight because we have a mesh of 2 millimeters. And so you have arthropods like mites or springtails or Protura, no, here, Symphila and other arthropods, and also Enchytraide, that is annelide, but we talk only about arthropods, microarthropods. And that is very important because it's a huge animal biomass and diversity in soil. In soil, you have 60% of biodiversity in that is in biosphere, and terrestrial arthropods, that's a huge weight in biomass, more than human, on mammals, wild mammals, and so on. So the project is enhance native soil biodiversity through the use of bioinoculants. To use this consortium of different bacteria and mycorrhizae to exploitation of native soil biodiversity and to have a feedback to the farmer. Today, we focus on biological soil quality. For other aspects, sustainability, economic, and quality, chemical and physical quality, you can go to the website of the project or ask me at the end. So the experimental design is, we talk only, we have 13 experimental sites out of 30, and 2 treatment out of 37 treatment, okay? That is only a focus with AMF, with or without biofactor. Biofactor is Vinassa and compost and so on. If we compare integrate pest management and organic management in 3 crops, apple, strawberry, and processing tomato. How to measure mesofauna diversity? That is important. We talk about ecological indices today because we have a lot of parameters in the talking about diversity. But for example, abundance, biomass, or respiration is not a measure of biodiversity. of course, and is in carrying capacity index, but not biodiversity. Richness, for example, is a quantitative index where everyone is different. But in our opinion, the best results we can have when you weigh in differences, when you group and you have depending to the function O2, in this case, the level of in soil adaptation. So we use this method made in Professor Vittorio Parisi in 2000, more than 20 years ago, is weighted on evolutive soil adaptation. So arthropods are different characteristics, small dimension, reduction of pigmentation, reduction and loss of eye or wings, and reduction of antennas and legs, and so on. Depending of this morphological characteristic, we have a morphological index that can have epigeal, semi-edaphic, and euedaphic biological forms. So, because euedaphic animals are more sensitive to the impact of the in agroecosystem. We talk about horticulture today. So the here maybe is a little bit specific. The index count all the group. In some groups like springtails, Conlembola, you take only the with highest adaptation. We try to use, and we present here a new index that count all the biological forms. We sample one cloud of 1 square soil decimeter cloud from soil, and we extract with Berlese extractor, very old extractor made from Berlese, with tool grind insert the lamp. With the lamp, you animal move and go through the funnel into the preservative ethanol, preservative liquid that we can assess in by stereoscope and classify symphyla and larvae and so on. That's just we arrived to the results, and in the whole project, a total of about 5,000 animals is we identified in 33 different biological forms from 130 soil sample. So this is the comparison. Okay, each point is a ratio between the untreated control and treated with mycorrhiza. So we can see, and we one, you have no effect, no? More than 20% increase, more than 20% decrease. So we have a gain in 71% of the cases, and more in the case of without effector. This is a little bit strange, but after I try to explain our hypothesis. But the important is both integrated pest management and organic management is more than 50% gain. But we try to considering only the strong, when we consider only the strongest change, the more than 20% increase. And we can make a focus on inorganic management, because you see in tomato fields, for example, in that case, we have only one case that is the decrease, but that it's normal, because in the apple orchard we have a permanent crop, and the effect of mycorrhiza can have more time to the effect, the impact, the beneficial impact on soil fauna. But it's interesting that the airway affix frequencies of biological form is higher in IMF in particular. Regarding the epigeal one, you have in some case more with biofactors. So because in
Finito.
addiction.
Cioè, non è ancora finito. Ma...
What? Okay. Sorry, it's not for me. The difference, as I said, I have an increase higher in apple than in strawberry than in tomato. Because we have less mechanical disturbance. That it's, of course, in the community structure of microarthropods, it's very important, the mechanical disturbance. And so, in the conclusion, I have 1 more minute.
1 minute.
Okay, perfect. The bioinoculant increase the diversity in most cases, so we can have a good result, because it was not sure. I mean, the link between mesofauna and inoculants. So this soil food web is very complicated, and to have some good results is that we have a reliable index to highlight this effect that can help to assess, because for our survey, for example, farmers know the biological indicators, but the problems is to assess the results. It's easy to assess if the pH of conducibility of soil, of texture is different. Every farmer knows, but maybe don't know if you have a protura and pauropoda is not so easy to understand. But and it's more effective in a longer crop system. So this is a preliminary results. It's a very small part of all the project, but is very. We are very happy to present it. Thank you very much.
Okay. Thank you. So, perfect. Now we'll have 2 more presentations on the Daily Soil project. We hosted a meeting of this project just this morning in this place, and we have time. I recommend the time because are near the limit time of 5. So I invite immediately next speaker. That's Caterina Grimonti of University of Parma. She will speak about soil improvers from food processing, residues, streams, and living labs. Please, you have 10 minutes.
Hello?
Something less than 10 minutes you have to also.
I will illustrate the project Daily Soil. And Daily Soil is an European project coordinated by Luke, that is a research institution in Finland. The daily soil started on 1st June 23 and is coordinated by Natural Research Institute of Finland, and the consortium is constituted by 40 partners, including Switzerland and Norway, that are outside of European Union. There are 7 work package. The work package 1 is a survey of food industry processing residue stream. WP2 is maybe the more experimental work package and concern the soil health improvement. WP3 enable for converting food byproducts and waste to soil improver and fertilizing products. WP4 concern the environmental risk and sustainability of this soil improver. And WP5 concern living labs that some of you were present in the meeting of this morning. And WP6 is dissemination, exploitation, and communication as a result that are common goal of European project. And WP7 is project management. Okay, the soil, daily soil is, the topic of daily soil is specifically soil health, because soil is is the substrate in which organisms and microorganisms grow. And so soil is important not only for microorganisms in the substrate, but is important also for environment and for agriculture, because of course an healthy soil promote the growth and productivity of crops. But the project Daily Soil have double two goal. It is inserted in the environment, in the background of sustainability, because it is inserted in the concept of circular economy and in as I already said, in the soil health. This a goal of this project is to get the objective of European Union to get zero waste in the 50. Okay. So now I will talk about the activity of the V-Soil that we are conducting at University of Parma and in cooperation with SINSA, that is Italian Consortium of Environmental Science, and the activity in this context are coordinated by Professor Marmiroli. Okay, in this activity, we considered 3 food chain, 3 byproducts of 3 food chains, and 1 grape pomace, tomato peels, and olive pomace, 3 food chain. And from these byproducts, we have produced compost. Compost is a traditional production, and in other case, we treated these byproducts through pyrogasification for biochar production. Biochar can be produced with two kinds of processes. One is pyrolysis and the other pyrogasification that are similar but are not the same. Pyrolysis or pyroscission is a process of thermochemical decomposition of organic materials that is obtained through the application of heat for 800 degrees in total absence oxygen. Pyrogasification otherwise requires a little oxygen contribute and occurs at higher temperatures. Okay, what is biochar? Biochar is the subject of study from several years because it has several beneficial properties. Biochar is useful because it can capture toxic elements in the soil, so you have effects of bioremediation of soil. It can be a carrier for transfer nutrients to plants and has other good properties. An important properties of biochar is protecting the rhizospheric bacteria of the soil from an adverse environmental condition. Effectively, in one work in this in a previous project, we have observed that in presence of biochar, some bacteria that were inoculated externally can survive better in presence of biochar than in absence. So this beneficial effect on bacterial soil is consolidated. Bacterial of soil are beneficial because they contribute to degradation of organic matter, and so they provide nutrient for microorganisms and plants. Okay, so we have we obtained char from tomato peels, grape pomace, and olive pomace. And these char were characterized to exclude any possible danger for the environment. So we have conducted test of phytotoxicity, test of genotoxicity, and we performed chemical analysis to exclude the presence of heavy metals or other danger contaminants. We have tested the biochar on two tester plants of agronomical interest, wheat and tomato. And we conducted this experiment, this test, before on greenhouse in more controlled situation, and after in field, and precisely exactly at Podere Steward near Parma. Okay, in greenhouse, we collected some samples of soils at T0 before the planting or sowing, 30 days after sowing, and 60 days after sowing at collecting of plants. And we performed chemical analysis of soil, microbial growth activity, and after that, we analyzed the plants, the performance of plants. Okay, after that, we have conducted field experiment on tomato, and they were conducted at the Stewart, and we tested the performance of plants, the soil health with this biochar, and in biochar with some microorganisms. And we collected some sampling, and we will conduct the same analysis that we have done with the greenhouse experiment and plant analysis, in particular productivity and quality of collection of tomato. Moreover, we planned the field experiment of wheat, in which biochar will be combined with compost to assess the eventual synergistic effects of compost in presence of biochar. Okay, just an important things. In this project, living labs and lighthouses are important aspects. Living labs are the possibility of farmers or enterprises, food industry, to test the results of research. Lighthouses are places for demonstration and peer-to-peer learning that share good practice. In particular, I show you an example of living lab in our research units. We have living labs, we have the side stream residual providers that were tested in laboratory, analyzed in laboratory and tested in field experiments. And these products, this possible amendment will be tested also by farmers that can be evaluate how these soil improvers are competitive in terms of productivity and cost with respect to traditional fertilizers. And in the same time, the provider of residuals can evaluate the value of their byproducts. Thank you.
Thank you. Excuse me for the rush, the final rush, but we are very, very short. Thank you. And so the last presentation, always on the Daily Soil project, is from my ex-colleague Anna Maria Berivino of Enea. And she will speak about microbiome-based innovation and soil improvers.
Okay, thank you.
10 minuti per 10 minutes. Yeah.
Okay, thank you very much for the invitation. At the end of the presentation that my colleague Caterina presented you the project Daily Soil, so I focus the attention on the microbiome-based innovation, soil improvers for agri-food sustainability and healthy soils. In particular, my speech will focus the attention on soil microbiome, how we can choose the efficient inoculum for sustainable agriculture, the scaling up production from laboratory to bioreactors for field application, the modality of the application, and at the end, the best practice for soil health and sustainable agriculture. The microbiome are very well in the agri-food sector, and in particular, the attention on these iconographers of microbe support action demonstrate the important role of the soil microbiome for sustainable agriculture, for healthy soil, but also for food quality. And the soil microbiome represent a key player on sustainable agriculture for their main role on ecosystem function, or the important role on decomposing organic matter and nutrient cycling and so on. So in this last decade in particular, there was an increasing attention on the use of soil microbiome for sustainable agriculture, but also as biomarkers for soil health. In this In this picture, you can see the different soil health and soil function processes and soil properties, and the microbiome represent an important, have an important role on defining the soil health indicator. So during the European Joint Program Soil, and we identify a new definition of soil health as a function, as a vital living system. So that means that we have to consider also the soil microorganism included into the soil. And the soil represents an important loop that combine the healthy food, that the human and healthy soils in the context of the One Health. And the microbiome solution also in these last decades represent an important aspect at economic level, because we can see the $6 billion invested in agriculture, in production, in bioproducts for agriculture respect to the other sectors. So it's important to invest in this sector and also to ensure the soil health and quality. But the problem is that when we move from the laboratory to field, you can see that in field we have different aspects that, for example, environmental impacts, experimental size, that affect the reproducibility and efficacy of the application of the biosolution. So in SIMBA project, we define two modalities to define the efficient inoculum. In this slide, you can see the SynComs versus NaturComs, synthetic assemblage of compatible plant growth promoting microbes respect to synthetic combinations of indigenous bacteria. And we perform in parallel this synthetic and natural combination and test in greenhouse and field. We publish these works, and you can see our important results on the assemblage of synthetic community and natural community. And also in SIMBA project, we apply this synthetic community in combination with biochar and bioactive compounds. And also we define a new culture medium for the scaling up of production using the pre-peer running waste in the context of circular economy to reduce the cost of the production of the inoculum. And you can see the scaling up of microbial consortia production from the laboratory to bioreactor, and also the freeze drying and air drying on zeolite for the field application. We tested in the SIMBA project different delivery systems, starting from seed coating to liquid suspension to biochar in collaboration with colleagues from University of Parma, stabilization with zeolite, and coated seeds applied in Italy and in Germany. And in this slide, you can see some our publication, and others are in press. And also the guidelines for farmers that we release at the end of the SIMBA project, in which the farmers can find the specific guidelines for testing plant growth promoting microbes in order to ensure the efficacy and reproducibility. And also the our SIMBA microbial consortia was identified by European Commission as innovation radar, and so are directly scalable to pilot scale and ready for commercialization. In the soil, I move quickly to this project in which we will use this microbial consortia in combination with different soil improvers, as Caterina mentioned before. So the improve, in particular, the aim of our patch 2 is to combine these tailored soil improvers from different food processing residue streams in combination with the most efficient inoculum. And first of all, in our project, we perform the data mining in order to evaluate, in particular, in the last European project, including SIMBA and other European Joint Program Soil, other projects funded by European Commission, the effect of soil improvers on soil health. And in particular, we analyze 60 project papers and performed the R scripts that identify the importance of biochar and biochar fertilizer yield at the end of this heat map. And in particular, as you can see, the microbiome, the microbiology is at the end of this circle. So that means that it's outside the main interest of these important European projects. So also we release the best practice in this deliverable. That means the application biochar, compost, digestate, other soil improvers has demonstrated significant improvements in soil health, metrics, crop yields, and environmental sustainability. And we published 2 papers on sustainable strategies and also culturomics and metagenomic strategies to follow the application of microbiome for sustainable agriculture. So in conclusion, we can use microbial consortia in combination with biochar and biostimulants and other bioactive compounds in order to reduce the chemical inputs in agriculture. And we can demonstrate this ability to scaling up these microbial consortia for bioreactor for field trials, in particular reducing the cost of production by using waste like Opuntia peer, and demonstrate the application. We aim to demonstrate during the soil project that application biochar, compost, and other digestate in combination with microbial consortia will affect the soil health metrics. So this, at the end of this my speech, I underline the strategy importance of microbiome-based solutions and soil improvers in soil management for sustainable agriculture. And also at the end, I focus the attention on the microbial culture collection. We launched this microbial culture collection 3 months ago. We have 1,500 strains from different sector. In the agriculture, we have a larger collection, nitrogen fixing, solubilizing, phosphorus solubilizing strains, biocontrol agents that can be combined in different combinations to construct synthetic community or target microbial community. Thank you very much.
Thank you. Perfect. Thank you, Anna Maria, for your presentation. So I think that as a conclusion, the first thing is I would thank all the speakers here and online, and you for attending this workshop. Just a minute for a keyword. The speakers showed and shared a lot of examples of innovative systems and techniques for nutrient and water recycling in order to improve the soil health. This is a key issue for the development of bioeconomy, and we think that the importance of this workshop is the possibility for establish future networking among the different projects that have been showed in this afternoon during this workshop. So thank you very much again to all the speakers and to you for participating, and I would invite you to stay for the next workshop that will start immediately after the conclusion of this one. Thank you very much.